Okay, welcome back. So last time we talked about using anion and using K-type chain to generate Majorana zero mode and use them to braid to do topological quantum computation. And there are something missing in the sense that non-Clifford gate cannot be implemented in a protected way. And I mentioned magic state distillation could be used. So we're going to see that in today's lecture. And then I'm also going to introduce the surface called quantum computation. I want to note that this way of doing quantum computation is one of the projects that Google is heavily invested. Okay. Okay, so I hope I can finish week 8's topic today. So let me start by looking at arbitrary phase state. I define this as an arbitrary phase state, but have equal weights of 0 and 1, but with different phase. And it is interesting that if you can have this state, you can use it as a resource to implement a general phase gate. So the phase gate I denote as U theta. Theta is the angle in this phase state. Okay, so we're going to see how it goes. And suppose we have a state psi. We want to apply U theta, okay? But we don't want to do it actively. It could be that we do not have a protective way to do that. And the only thing we can do is the usual Clifford gate. Okay, so assume Clifford gates are of high fidelity. So we want to use A theta as a resource. So we just put the two states next to each other. So assuming the psi is A0 plus B1, and I want to expand this. So A0, 0 plus B e to the I theta 1, 1 plus the cross term A0, 1 with coefficient phase e to the I theta, and B1, 0 with coefficient 1, but I want to extract overall phase e to the I theta here. Then I see that this is e to the minus I theta. Okay, so far this is just algebraic manipulations, but what we're going to do next is to measure the stabilizer ZZ, and this is a valid measurement in a Clifford way. So suppose we measure that. So here we do not worry about how to implement that physically, assuming we can measure that. And we know the ZZ stabilizer applied to 0, 0 and 1, 1 is 1. But if it applied to 0 and 1, 0, it get a minus sign. So therefore the measurement, when you get a plus eigenstate, you're actually projecting to this subspace, therefore project the state to A0 plus phase times B times 1, 1. This plus eigenspace. And this is minus 1 eigenspace. Okay, so you have two possibility, the +1 and -1, each occur with probability 1/2. So if you get a +1, then you are in a state, entangled state, like this. So if we apply the CNOT gate, then we disentangle the second qubit to 0. And so this is what we wanted, right? This is an effect of applying the theta gate. So in fact, we achieve this, right? With ancilla return to 0. Okay. If we have the minus case, the phase is the opposite. Okay, but we can still perform the CNOT to disentangle the ancilla, and we then apply the minus gate. Okay, but this is not too bad because randomly you get plus sign or -1, and you can assume there's a random walk. If you get to 1, then you stop, but if it's -1, you will keep branching out to see if you get a +1 or -1, and you run a random walk, there will be finite probability that you would get back to the +1. So this is going to be a probabilistic procedure because you are going to use many copies of A theta, but you know when you succeed. So in this case, you measure +1, then you stop. You declare that I have successfully applied the U theta. If not, I have a minus action, then I want to actually, if I could apply 2 angle, that could also be useful. But if not, I can apply the same phase state, combined with the same phase state, and I wanted to return to the origin, and from the origin, I start again. Okay, so this is going to be a probabilistic procedure, but we know when we succeed. Okay, so that's the idea of magic state distillation. Is you want to have this kind of state, which is of high quality. So the quality of U theta depends on the quality of the state. Here we assume it's like a pure state, perfect, with the phase e to I theta, but it could be decohere because of the noise or other coupling to the environment, etc. So the idea is that if we have particular state, for example, we want to choose a particular state, the H state is defined as this. This is defined that as such that the Hadamard gate acting on H is a cell, because it's an eigenstate of Hadamard gate. This is the explicit form, and you can show that if you apply the phase gate, this is the phase gate, just our usual phase gate with pi/2. So this is I here, and this is arbitrary phase gate. This phase gate S is in a Clifford. So if you apply S and then Hadamard, you can see just by putting a phase here, for example, the phase gate would put this, and Hadamard would just combine cosine pi over 8 plus I sine pi over 8 in one case, and the other case we'll put a minus sign. Okay, so I'm explaining the action of this HS on H state, and this turned into a phase e to the I pi over A and e to the minus I pi over A. So if you extract these, or the overall e to the I pi over 8, this is nothing but a phase state with the phase minus pi over 4. Okay, so from this, we can implement a non-Clifford gate. This is the dagger of our usual T gate. So our T gate is defined as this. However, in this paper, the T gate is defined differently. So I will use T tilde to denote the T gate in the paper by Braid and Kitaev. Okay. So that's the use of a H state. And if we consider another state, T state with some coefficient, cosine beta, sine beta with a phase, and the cosine the beta satisfy this equation. So I'm going to give you the meaning of this T gate, but I want to first ask, can we also get a useful phase? Can we also get a useful phase gate? Okay. So in this case, we're going to do it slightly differently. We're going to make 2 copies of that. Okay, actually what I'm doing here is I really want to get a phase. Yeah, sorry, I really want to get a phase state. And from that, I can get a phase gate. Okay. Yeah, so the phase state from the so-called magic state H is this A minus pi over 4 through the action of Hadamard and the phase gate. Okay, and these are Clifford, so that's what we can use. But suppose we have this T state. It's not quite in the phase state that I defined earlier, because I defined so that it has the same weight except the phase. So can I get from this state to get some useful phase state? Okay, so that was the question. So in this case, I will start with 2 copy and measure similarly the stabilizer. And this time I only keep the +1 outcome. You can check this will succeed with probability 2/3. When it succeeds, you obtain this state, because remember we were expanding. So if I want to put in more detail, you expand this cosine square 0, 0. Let me do it step by step. So you take the 2 copy, and we only want to select the plus eigen state, which is the combination of 0, 0 and 1, 1, right? And the 0, 0 coefficient is cosine square. The 1, 1 coefficient is sine square, and also the phase is double to e to the I pi over 2. Okay, this is when we get the +1 outcome. And you can see that this is a cosine pi over 12, 0, 0, and I sine pi over 12. So you have to verify yourself. So anyway, it's a cosine angle and sine angle, and with this I. Okay, then you apply control NOT to disentangle, and then you apply the Hadamard. So the reason to to use the Hadamard is it would mix the two, right? Just like in the previous case here, if I put a phase gate S, then I would have I here. Then if I mix the coefficient, either plus or minus, I get a phase. So here we're doing similar things. If we mix the two coefficients, it will become e to the I pi over 12 or minus pi over 12. Okay, then this is a phase state that I defined earlier with the angle minus pi over 6. Okay, so this is also going to give us a useful phase gate, and this is also non-clipper. Okay, so just to remind you, the A minus pi over 4 is non-clipper. Okay, just remind you the clipper gate. Let me just call it GC. Clipper gate map a poly to another poly. Okay. Okay, so we can see that H and T are two special states that can give minus pi over 4 and minus pi over 6 gate. So maybe let me go to this slide first. Yeah, so this is what I promised to you earlier. So the T state, if you write in terms of density matrix, has this nice geometric interpretation that this is at the corner of this shape here. So this is coordinate 1 over root 3. So at the vertex here, and the H is at square root of 2, 0, 1 over square root of 2. So it's somewhere, if you draw a big circle, it's this location. Okay. And the clipper gate, single cubic clipper gate, simply move, or I mean just rotate T and H. Okay, so what you see on the right side of this figure is that the empty circles represent the T type. These are the T. This is looking from the top, so this is looking from the top. So you see the XY plane, and this is H type. Okay, so all these are equivalent. So meaning that all these are useful state. So H, T type states are useful, as we have seen earlier, right? So, but it's interesting to see that these lies outside this octagon. So there's an octagon spanned by the 0, 0, 1, 0, 0, minus 1, and 1, 0, 0, 0, 1, 0, etc. These 6 eigenstates of polymatrices, they form an octahedron, sorry. And the state inside this octahedron are useless because these are they are mixture of 0, 1, plus minus 1, I minus I state. Okay, so natural question is to ask what are the useful region? Of course, it has to be outside this octahedron. And we have identified, for example, these H-type and T-type state. These are clearly outside the octahedron because they are of radius of length 1. They are on the sphere, but they are not on these 6 vertices. Okay, so, and we have seen that they are useful because they allow us to implement these non-Clifford gate, minus pi over 4, minus pi over 6 gates. Okay, so the point of this paper, which is a bit technical, is that we can generate high fidelity H and T states. So I won't describe the procedure. This could be in itself a paper if somebody want to present in a final presentation. So they use a particular 5-qubit error correcting code for the T state. And they show that if you start with, if you were able to create a noisy state that is close to T in the sense of this is fidelity, and 1 minus that, that's called infidelity. If the infidelity is low enough, meaning that this T state here, and if you have some noisy state, if they are not very far, if they are close enough, then this row is useful, can be used to distill a single high quality T state. And you need a many copy of noisy state. And for the H state, you have to use a different, they use another error correction code. It's of the CSS type. And they show that if the infidelity to this H state is small, then you can also distill high quality of the H state. So I have typo here, so maybe I correct typo. This is noisy. Okay, so basically there is a procedure first proposed by Brabi and Kitaev that if you use take advantage of error correction code, and if you have a noisy state which is not far from the T state nor the H state, then it can be used to distill these states respectively. So the procedure is complicated, so I don't want to describe that here.
But are 0.173 and 0.141 the upper limit? Yeah, the upper limit for the infidelity.
This depends on what error correction code you use. So they know that if it's close enough, in the sense of fidelity less than this, it certainly can be used to distill. But if it's greater than that, in that paper, it doesn't, you cannot say anything because unless you prove that it's definitely not useful, unless you could do that, there might be someone using a different error correction code that would allow you to achieve that. So definitely, as long as you are out, what you can say for sure is that if the state is inside this octahedron, then it's definitely useless. And they were hoping that maybe every state outside of that could be useful, but they only prove this limit. Yeah. Okay. These two limit does not agree with like it's not like on the surface. Okay, so there's still some distance.
Thank you.
Okay. So the upshot is that if you have a noisy state, that noisy state you could create by a noisy gate, and the noisy gate may take you not quite to T, but close enough. If that's possible, then you could start from there. You could have many copies of the noisy state, and then it can distill very close to the ideal T state. Okay. And once you have the ideal T state, you can use to implement the -π/6 gate. Okay. So of course it requires a lot of resource, but it's not exponentially large. It's still manageable resource, but it's still not. Maybe it's still probably better than using concatenation of error correction code. Okay. So any question on this part? So maybe a summary of the magic state distillation is that maybe the summary is this: use noisy gate to create states close to T and S. So close in this sense, close in this sense. Okay, close in this sense. If you were able to do that, then can distill clean T and S, and from that can implement high fidelity non-Clipper gate. Okay, so once you have high fidelity non-Clipper gate plus your maybe protected Clipper gate, then you can have protected quantum computation. Yeah. So this, if it applied to the Ising anion, and if the noisy gate, noisy non-Clipper gate can allow you to create T and S state close enough, then this Ising anion would be useful for quantum computation. So that is one motivation to use this magic state distillation. Okay. Any further question? Okay. So next, I want to move on to surface code. Surface code has the issue similar to the Ising anion, that their gate set does not include any non-Clipper gate. So therefore, you also need to do the magic state distillation. So this is why I introduced the magic state distillation in the beginning, because firstly, it solved the Ising anion problem. And secondly, it can also be used to solve the surface code problem. And surface code is an artificial topological code, but it can be easily implemented, or at least easier than finding the Ising annual. Okay, so that's why this surface code so far is the one that's highly studied. Okay, so but this code is essentially the toric code, but on a planar geometry. So remember that the toric code has the star operator, which for a vertex, it acts on the 4 nearby edges, the qubit on these edges, in this XXX part of X form. The plaquette operator acts on the 4 qubit surrounding a plaquette. Okay. So for example, there will be a plaquette here, BP, and there could be a star operator, AS. But the star operator, if you look at the sort of dual picture, there is also a plaquette on the dual lattice. So if I draw this as, I call this D bar, the plaquette D bar, I can just represent this as a product of X on the boundary of this D bar. If I call this P, then I would say the BP is simply product of Z on the boundary. This is just a shorthand notation for this. Okay. The difference is that in the surface code, I don't have the torus, so I don't have the ground state in the sense of topology, right? So in order to encode a logical qubit, I should create a topology myself. And in this case, it's to punch hole. Okay, it's to punch hole. But what I mean by punch hole is that if you look at the example, we see that you create an excitation, a pair of excitation of charges, or pair excitation of fluxes. In this case, we're going to use a pair of these, for example, the plaquette, as a way to encode a qubit. To do that, what we want is that we want to remove the two stabilizer, BP and BQ. So on the toric code, for each plaquette is a stabilizer. So violation is minus sign, etc. But in the surface code, we want to punch hole to this plaquette in a sense that I don't want to enforce the constraint, meaning that this BP here is not a stabilizer, this BQ here is not a stabilizer, but instead I want the product is a stabilizer, right? Therefore, I remove two constraints, put one constraint back. So I have one constraint less, so therefore there is a qubit. There's one qubit that I can encode. Yeah. Then for the pair of charge excitation, or the pair of star, we call these defect because these are the stabilizers that are removed. So for a pair of the stars, let's say U and B, so I don't want to enforce, we would remove the constraint, meaning that it's not required that AU act on the code space is +1, nor require AV act on the code space to be +1. We only require the product is in the stabilizer. So similarly, there's also a 1 qubit that you can encode. Okay. So then you can ask, what are the logical operator For example, since this is not in force, so therefore the product of this operator is not in the stabilizer, and it commute with the stabilizer. So I can take this as the logical Z. But I can also take this as a logical Z because the product of the pocket P and this is 1. So yeah, so the product of Z, the two plaquette, is one that's in force. So you can take either one as a logical Z operator. Okay, and to find a logical X operator, you need to find one that can be with all the stabilizer operator, but anti-commute with the Z operator. Okay, one natural choice is the product of X along this line, because the red pocket are no longer stabilizer. So for all the other pockets, these X string cut cross twice. So therefore, Z anti-commute with the X anti-commute with the Z bar, but commute with all the stabilizers. Okay, does that make sense? So in the case of the charge defect, these are not in force. These are not in force. So I'm going to take this because this operator and these two operator, they all commute with all the stabilizer, and they anti-commute with each other. So I want to choose this product of Z along this line as my logical Z, product of X surrounding the dashed line here as my logical X operator. You could also choose this as logical X operator because they are equivalent in terms of code space. Okay, I mean, you could, in the pocket case, you could swap the two, which is fine. But the reason we choose this as a logical Z is because this is product of Z, and the line is a product of X, so we label as X operator. And here, this is a product of Z operator along the line, so we denote as a logical Z operator. And this is a product of X operator around this loop, so we denote as a logical X. So the choice of being logical X of Z is arbitrary. So any question on this? This is probably the most important starting point. So in the Tori code, we use this like product of maybe X, product of Z as one logical operator, right? And the other one is we choose a product of Z operator, and then the other product of X operator. Okay. But here we do not have this topology. So we sort of use the effect to mimic that effect. Okay. Okay, so actually I said that, so, but let me just reiterate because this is very important. So for a pair of plaquette defect, sometimes this is called primal defect because removing a plaquette from the lattice. So I choose the logical Z operator as product of these 4 Z's on this plaquette because it's no longer constrained, meaning it's no longer in the stabilizer set, but therefore it of course commute with the stabilizer. And this one as well. The only constraint is the product of these two plaquettes is is 1, so it's in the stabilizer. So I can choose this as a logical Z, and then I just need to find one that anti-commute with my logical Z, but commute with all stabilizer operator. And the natural choice is this line, meaning X cut across all these, okay? This is also called, the logical qubit is also called primal qubit. So the dual qubit is using a pair of star defects, and the natural choice of logical Z is this line, the product of Z operator along this line. And therefore the X along this loop is my logical X. So this X is equivalent to this X. So X okay, so this one here is equivalent to product of Z operator surrounding the Q plaquette. Okay. So in the following, if you can have a pictorial way of understanding, then that would be very good. So if you don't get the detail, at least get the picture. Okay. So first, I want to say that this definition of logical operator has a lot of freedom. For example, we can move the logical pair. We can separate them. For example, to do that, in order to take this logical qubit and deform, for example, you want to move this Q to the next site. The meaning is that then the next site, the plaquette operator should not be in the stabilizer, but then this one should be. So the way to do that is you perform an X measurement to break this plaquette operator, and then you measure the Z plaquette operator, and that will restore that it's been in the stabilizer, and then this one will not. Okay, but that's really a sort of detailed implementation, how you move the qubit defect around. You can, but the upshot is that you can freely move these defects. If you don't encounter any defect in between, then you can freely move this. So I can move this plaquette to the next site. I can move this charge to the next site. So in this case, in more detail, what you do is you perform the Z measurement on this qubit, and then you measure in the X stabilizer to restore this being in the stabilizer set. And this one, because the measurement Z would make this not in the stabilizer set. Okay, but this is detail, but the picture is that you can move the defect. Okay, so I'm using the simplest example. The defect is just one plaquette here, another plaquette there. Okay, but the next slide illustrate that actually you can make this region bigger. Okay, to make it bigger, in a sense that the stabilizer, plaquette stabilizer inside here is not going to be enforced. Therefore, you can use X measurement to expand this region. Okay, but just the picture is that you can expand as long as you don't swallow other qubit pair. Okay, so you can expand the plaquette. You can also expand the star or the dual plaquette to a bigger one. Of course, you can do the reverse to string them. You can also, by using the this deformable, you can also move these two defect close to each other. Okay, you can also move these to very close to each other. Okay. Okay, so any questions so far? I was talking about the logical operator.
Yeah, why would you want to shrink or expand them?
You will see, because if you have only one logical point, right, then you can perform noisy rotation.
Okay, I see.
Okay, so for example, if my pocket operator is this, then I cut across these two edges. But if I sort of move next to each other, this is my logical X operator. Logical X operator is only a single X poly, right? Yeah, so this is a good question because I'm going to use this later. Okay. And when you shrink, and you could also apply operation on these four. You could also do any operation you want. Just for example, you can apply Control Z, etc. But these are not protected. They might be noisy. The physical Control Z between two physical qubits can be noisy. Okay.
Okay, thank you.
Sure. One thing I want to mention is that we have defined a logical operator. So what we want to see if we can prepare the state in this logical basis. So meaning, can I prepare, this is to prepare logical plus state, right? So to do that, if you start with vacuum, nothing, what you would do is you create a defect region. So to create a defect, basically just to break the stabilizer operator in that region. Okay, since we concerned with the plaquette, to break the plaquette operator, we just perform X measurement. Okay, so we just measuring all qubit in the circle in the X basis, and then we want to, in this case, all the hello, I think there was an internet issue.
Yeah, we can see you now, but we kind
Okay.
of lost you.
Yeah, it's fine.
Are you still recording?
Let me share the screen. So I was talking about creating logical state. Can you see this? Can you see my slide?
Yeah.
Yes.
Okay. Yeah, so I was just saying that you measure the X in that region. In a sense, you break the plaquette operator inside this region. And you can regard all these are prepared in a plus state. Therefore, these are eigenstate of X. And then you want to create the qubit, right? Because the qubit should be formed by a pair of defects. To create a shape of two defects, you sort of need to carve out this region, carve out the region. And by carving out, meaning that in this region, the stabilizer, the plaquette stabilizer should be in force. So what you do is you measure the star operator in this region. Okay, so I'm measuring in the X basis. So I'm going to measure the star operator to restore the stabilizer condition, and then I'm left with two separate regions. Okay, so because I already have a plus, so this string of X acting on those plus state is naturally in the plus state. Okay, so it's in the eigenstate. Okay, so I think maybe the picture is more important. The way to see this, the state preparation is you start with nothing and you start measuring, you create some region, and then you do some surgery and you separate the two defect regions. So this is representing the defect. Okay. Yeah, so the purpose of this lecture is to create a pictorial way to understand this, at least to remember what's going on using pictures. So basically, you can forget about microscopic detail. You perform some measurement and you create two regions. In the beginning, it's a one region, and you start to separate them, and these form a logical qubit. And this logical qubit, it will be in a plus state, logical state. Okay, and the arrow goes up in time. Okay, so this is just to prepare a state, we use measurement. Okay, and again, this is not topologically protected, okay? Because we use physical measurement in X, so it's not protected. The only thing that's protected is the CNOT gate. So I'm going to explain the CNOT gate in the following picture. So what I'm going to do is I'm going to take one of the defect, the plaquette, this plaquette defect, and I move around. So I move around this, do a braiding. So remember, the way I move around is I have to perform measurement and break the plaquette and restore that by measuring the stabilizer, etc. Right? But essentially, what's measured is the X operator. So you can imagine, similar to the torical case, we apply the X operator. Okay, so there is some X string that loop around like this, that representing the braiding. Okay, so we can ask, what does the braiding do? How does it affect the logical operator? Okay, first, does this braiding affect the Z operator? Because the Z operator, you have two equivalent ones. One is here, one is there. It's easy to just focus on this one. This does not change, right? I braid around, I have nothing to do with it. So this logical Z remain the same. So the error meaning that it does not change. There's also another logical X operator that remain unchanged. That's this one. Right? So this one okay, I denote as U, but it's actually V here. V doesn't change, but since V and U are equivalent, so U also doesn't change. Okay, so what comes next is probably the most important one, is how we analyze this. So I draw a green green curve, right? This representing sort of a deformation of this. So I told you earlier that you could actually use this one, right? Because you can deform. So I could choose any path between the two, right? But since I braid around, in effect, when I move this Q around, the string sort of go from here and wind around. Does that make sense? Right? So you can imagine you're moving this Q in a way that I'm deforming the string around this and back. Okay. And since this is a string, I can sort of decompose into one. So I can add this string and remove that in the sense that I have now decomposed the green line into two parts. One is this one, right? One is this one. This P connecting to that to Q, which is the X operator, X logical operator. But I'm left with another loop. This loop winds around this defect here. It's a X loop, right? It's an X loop around this U. So that means my logical X operator, after braiding around, okay, after braiding around, I am left with a logical operator C bar. It's deformable to this curve, and a loop around this defect. The loop around this defect is a logical X operator for this qubit, right? And because U and B are the equivalent, so therefore, the upshot of the braiding is that the logical X operator is transformed to the X operator times the X operator of this qubit. Okay. Well, I think this is probably the most important diagram in this lecture. So let me go back again. So I'm braiding this defect around the charge defect, right? So, but in terms of the string, I can see that maybe my string is becoming this and become and deform around. So this is what I draw. You could draw any other curve like that, it's fine. So I see my logical operator become this string, the green string, but I can decompose the green string into this part, which get back to the logical X operator and this loop, okay? Notice that this I use twice, so it cancels. So that's why I can deform into this string and a loop, okay? So that means the effect of that braiding is the logical X operator on the primal qubit become the X operator for that qubit and multiply by the X operator for the dual qubit. Okay, does that make sense? And I also want to see how the logical operator, so I already see the X operator for the dual D qubit doesn't change. What about the Z operator? So for Z operator, it's perhaps easier to explain in a relative view. So if I braid around this, it's in a sense equivalent to I'm braiding the U, the blue U around the red plaquette. Okay. Okay, but before I do that, this has a nice interpretation of the diagram. This is a pair of defect, a primal defect that define my logical qubit. And this is another pair of the dual defect define one qubit. I take the one of the defect and braid around the other. It doesn't matter which one is actually braiding, right? As long as you have this kind of topology. You could move both together simultaneously as long as you see that the space-time diagram looks like that, they braid around each other and return to the location. That is a braiding. And under this braiding, we see that the logical operator is changed. Okay, so we know this logical X operator is changed to this. What about the logical Z operator? So as I said, I'm going to use this sort of a dual picture. I can braid these U around this plaquette. Okay, if you accept this picture, it doesn't matter which one is actually moving, right? As long as the braiding here. I could be this one standing along and I take the blue one braid around, or I have this blue one stand still and the black one braid around. These are all equivalent. Okay. This way it's easier to explain. Okay, but it's not necessary. You could also you could also always stick to this picture, but I find it easier to explain, also to prepare the drawing, is I do this U, do it around. Okay, so in a sense that this logical operator, which is a Z operator, is product of the Z on this, has a string that is move around, right? When you move this guy to here, the string sort of deform to here. When you move and return, the string deform this way. The string is a Z string that deform this, okay? Then similar to the previous case, I draw another curve to break these into two parts. One is a cycle around the Q, which is a Z logical operator on the primal qubit. And the rest is a string connecting the two defects, directly connecting the two defects. Okay, so that's a logical Z operator. So this means that logical Z in the beginning is like that. And after the braiding, this I get back the Z logical operator. But in addition, I have a extra loop looping around these defects, which give me a logical Z operator on the primal qubit. Okay, does that make sense? Okay, so what does that mean? So remember we have these commutation relation, right? So the Z operator on the control qubit, when it conjugate by the control NOT or some operation, okay, assuming we don't know what this operation is, the Z goes back to Z for the control qubit, but the X become a Z on the control and X on the target. The Z of the target goes to the target Z target cell, but has additional Z on the control. The X pass through. So this is exactly what we found, right? My Z of the primal qubit become the Z, still Z on the primal qubit, but my X on the primal qubit, yeah, this is X on the primal qubit, becomes the X on the primal qubit and also on the dual qubit. Maybe it's probably visually better if I swap these two. If I swap these two. Well, yeah, I think this should be here and this should be here, in a way to match the picture upstairs. Okay. But this, what we have identified is that the action of braiding on the two qubits is a control NOT. But it's important to know that the primal qubit is the control and the dual qubit is the target. Okay, so that's probably the most important conclusion from this manipulation of these defects. Okay. But you could also ask, well, because I'm always using the primal as a control and dual as a target, then these control knot, they all commute. So it's not that useful if I don't have a control knot between the same primal pair or the same primal or the dual pair. Okay, this is a way to do that. So, but this is, you can regard this as a circuit identity. If you have a control bit and target bit, and if you can prepare additional logical 0 and logical plus, if you do the control Z on these first two qubits and the control Z using this as a control, and also another control here, and you measure this in the Z basis, this as a X basis, then this implement a control knot on this and that. So the target would be transformed to the third. Okay, this is a circuit identity. But now if you interpret that this as a primal and this is as a dual, because that's the only CNOT we can implement. This is the primal and that's the dual. This is the primal, that's the dual. And the target now become a primal. Okay. So, and this has the nice interpretation of the diagram. Let me interpret this. So the control in is these two. These two form a control qubit. We can only do the control knot on primal to dual. So the dual is here, but it starts with 0. So in 0, we talk about the preparation of plus state in the primal case, but here similarly, you start with vacuum and you start measure, and particularly maybe in the Z basis, and then you have a defect in terms of time slice. Then you have a pair of defect, the dual defect, and one of them is braid around with the control of this. Okay, and then you do a logical plot preparation, and this one actually is this one. It doesn't because the topology, it doesn't matter if you draw it here or you draw this loop further to the left. Okay, it's probably okay, and you can even deform the loop so that the preparation of the state begin much earlier. Okay, you could also do that, but then you can deform back to here. So this primal qubit is here. The target is here. This is the target qubit to begin with. And this is the measurement, right? So this is the measurement of this qubit. And this is preparation. So the preparation and the measurement, they are in a reverse way. So this is preparation, and this qubit braid around with the blue one, the dual one. This target comes in also braid around with this dual qubit, the blue one. That's this part of the braiding. Okay, so it has a nice geometric way, graphical way to understand this. Okay. Yeah. So any questions so far? Yeah, I want to mention I used this. I took the picture. This picture is from Fuji. I think it's archive 15 point something. I have that earlier in the slide, not in this one, but yeah. So this it has a nice explanation of what I told you here. Okay. So, and in fact, control knot is the only protected gate in the surface code. So how do we get? We don't even get other Clifford gates, protected Clifford gate. So this is maybe closer to what Yushin asked earlier. So how do we do the logical Z operation? So there is also a circuit. I don't want to verify the identity here. Is that you have a pocket, right? And there are 4 qubit. If I can prepare another ancilla, so adding a 5th qubit, but in a plus state. So remember, I can initialize in a plus state by just measuring the x. And then I perform physical control Z in this way. And before I measure out these ancilla qubits, I do a rotation in the x basis. And because it's a single qubit rotation, I can do it. It may not be protected, it could be noisy, but suppose I do that, and then I measure in the Z basis. Then the effect on this is a logical Z rotation, okay? So I don't verify this. Maybe I should, let me just put a memo, maybe create a homework for this. And also for the CNOT. Okay. Okay, unfortunately this is blocking the picture, but the picture is that if I have a pair of defect that is a logical qubit, I want to shrink this region so that it's down to a plaquette, okay? So when it's down to a plaquette, that's represented by this little circle. I could do this locally here. I could prepare a plus qubit next to it, and I apply these control Z gate, I apply rotations, and I apply measurement. And once I obtain that, I would implement a Z rotation. Then I expand my defect in a larger region. So the reason you want to use defect in a larger region is that the code space depends on the size of the defect. So that's why everywhere else in this, the defect are thick, they're protected. But this region is vulnerable, you are susceptible to noise. Okay. So that's the Z rotation. And also want to mention the X rotation. X rotation is easier. You bring the two defects next to each other, really physically next to each other. The logical X operator is only acting on a single location. So to do the X rotation, you basically just rotate that. So just, I should simply rotate this single qubit by X by some angle, okay? Then you expand it back. So this is a physical picture. I have a pair of defect. I want to bring them next to each other. So it doesn't need to shrink also the other. So the other side, so as long as you put them next to each other, the other direction could have some width, but this need to shrink to a single contact. So once I'm done, I expand the region. So then I can implement logical X and Z rotation. But as you can see, they are not protected because they are in a small region. The code distance is really small. But they are useful in the sense that they can inject noisy state, noisy magic state. And from there, we can distill on high fidelity magic state. Okay. Logical phase state. How do we create a logical phase state? Okay. So we have a rotation, right? So if we have a rotation, Victoria look like this. And I also mentioned earlier, I can prepare the logical state, right? This is preparation of logical X state plus state. If I create that, then I perform the logical Z rotation. In combination, this looks like that. In time, you prepare this, and you shrink this region, do the rotation, expand. So you have this nice diagram representing logical phase state preparation, right? So this is the state that I started with when I talk about magic state distillation. Right? So if I can prepare this state, and I go through the magic state distillation by Braid and Kitaev, and I could implement some non-Clifford gate. Okay. Okay. So I mentioned we have CNOT gate, but in this case, so in the surface code, we don't even have a good Clifford gate other than CNOT. So, but we can also use the same idea of magic state distillation. But the magic state that we need, for example, if we want to have an S gate, what we can do is to create a eigenstate of poly Y that would allow you to get the phase. So this would be just 0 plus I1. If you have that state, right, this would allow you to have a phase gate. So phase gate. Okay, but this is in the X basis. You can verify the circuit so that you see that you get a S gate, but in the other basis as X basis. Okay, this is the Z basis. Okay, so this is useful in the sense that I can not only do the diagonal gate, but I already have a rotation. Okay, but this is still Clifford. To get non-Clifford, we need the eigenstate of X plus Y, which is used to implement pi/8 gate. So that could allow you to get the, yeah, so this allow you to, yeah, so when we say pi/8 gate, in the language above, I think this is U pi/4. Yeah, unfortunately, that's the notation. This is really the H, this is really the H state, eigenstate of this operator. So, and this circuit says how you do that because we have a protected CNOT, so this part is clean. So, and we can distill a gate, a non-Clifford gate. Okay. So maybe this is a summary. So we have in the surface code we have protected CNOT, but we don't even have other gates. But these other gates can be obtained from magic state distillation, but that require more work, but in principle can be made with low error. And with these other gates, it can form a universal set of gates, and that will be useful if we can do that in the surface code. Yeah, and notice that you could also use the magic state distillation in the anion, Ising anion. So let me just put it here. Can also apply magic state distillation to Ising anion to make universal gate. Okay, and perhaps this is the reason, because to do the Ising anion, which is actually, maybe let me just put, this is where Microsoft is, what the Microsoft is betting on. So Microsoft want to implement topological quantum computation, but using the Ising anion. So that's why they invest a lot on finding these Majorana zero modes. Google, on the other hand, has adapted the surface code. These are not intrinsic, there's no material that would give rise to that. You have to engineer that. But this is, it looks also easy to do because you don't need to wait for some magic material to give you the Eisenanium. But here you simply engineer these qubits in a way that is compatible to the surface code. You can see the geometry that they are created is very compatible to the surface code or the toric code. Okay, so I guess that's it for today. Any question? Okay, if not, let me first remind you that the homework is due on Sunday night. And if there's no further question, I will see you next week.
Thank you.